the most recent stuff, which is fairly simple. But everything is simple because it's still low dimensional. But it's very important because once it becomes high dimensional, it won't be as simple anymore. So one here is the operations of functions, and so since everything is linear, it is fairly straightforward. So adding two functions to linear functions is straightforward, and doing compositions with two linear functions is also okay. Multiplying two linear functions produces a function which is nonlinear right there in the middle, so we do not do that operation. However, like I said, addition and compositions are okay, as well as scalar multiplication, meaning that you multiply a function not by another function, but multiply by scalar, in other words, a number. Okay, so that's the terminology we're gonna use plenty. Okay, so that's we more or less finished with that. So just the main ideas. Once functions become multidimensional, or rather the input is multidimensional, output is multidimensional, then everything, all these simple ideas will become less simple, and so that will be the challenge. And the next topic is to look at functions in a different way, and that is not. I'll get to that later. But what I want to talk about is functions as transformations. So once again, in lower dimensions, it's easy to handle. So that's where we start. So functions as transformations. Okay, so, well, we'll just take a few functions that are familiar and look at them as transformations. Transformations of what? Of the domain into the codomain, or the range. Codomain. So y equals x squared, the graph is this. And then graphs are good for visualizations of functions, but so this is x, this is y, and the trouble with graphs is that they are located in a piece of paper, which is kind of a two-dimensional, and then we might have a third dimension also available for us to visualize things, but unfortunately, once we go to dimensions higher than 1 and 1, so this is dimension 1 and this is dimension 1, the graph also goes up in dimension. So if you have input two-dimensional, output is one-dimensional, the graph will be located in a three-dimensional space. And if you have 2 and 2, it will be located in the four-dimensional space. And so we cannot really see it easily or visualize or draw on a piece of paper or even in space. If we can, well, maybe one day we'll be able to draw things in like three-dimensional way, but it's still not enough. So one thing to help, so a different way of looking at functions, it is as transformation. So what has happened here, we take our x-axis, so that's the domain, and then every point in the domain is taken by the function into a point in the codomain or the y-axis or the output. Okay, and so if you can just describe what happens here, you could visualize, at least in your mind, what's happening, what that function does. With this function, it's slightly complicated because it's not a linear function, but you can say that what has happened to the domain as a whole. What has happened? The domain was a straight line, the x-axis. What did we do to it? What?
I mean, like physically. Like
yeah, physically. So if you imagine a piece of wire. Here, okay, here it is. Okay, so this is the x-axis. What did we do to it? What?
Bent it upwards on both sides.
Oh, that's right. We not just bent it, we folded it like this, and we made it that's the y-axis. What's left of the y-axis, right? So as you can see below the x-axis, there are no values of the function. So the range is this. So this is the range, and this is the range. So from the whole domain, we create from the whole domain we create the range. How? By this roughly this way. Not exactly true, because there is an extra operation going on, and that will be some stretching of the branches, right? So because, for example, 2 goes to 4, right? So farther away. So if this is 2, it does not end up at the same height here. It will be at 4 height. Okay. So fortunately, that's not as hard when we deal with linear functions. So let's take a look at what linear functions do, and we can fairly easily classify them. So say y is equal to 2x. Okay, so this is the graph. Once again, we still can plot graphs, so that's why I want to use them, but I wanted to describe it verbally or otherwise what's happening. So we have described y x equals square. So let's say x-axis is folded in 2. Okay, so that's roughly what y equals x squared does. Okay. The x-axis, once again, you can think of it something physical. As we go up to dimensions, then instead of x-axis, we'll have xy plane. It will be a plane, and we'll ask ourselves, what do we do to that plane? And once again, we can fold, we can turn, and so on. So we'll get there. But at this point, let's suppose we're talking about a simpler linear function, y equals x squared. Y equals 2x is our function. And, okay, so what does it do? Well, first of all, the turn is really not a part of the operation, because it is just a matter of how we locate x-axis with respect to the y-axis. We could just as well locate them like this. So this is the x-axis, and this is the y-axis, and then the whole x-axis then ends up like this. It's called the image. Okay, so the image of the x-axis ends up, so say 0 goes to 0, but otherwise there is this folding operation going on. So x and y-axis were put in a perpendicular directions to each other. It's just a matter of convenience, and that's we're using the Cartesian system. But other than that, when we're describing what one does to the other, they're like, you can think of them as if they are living separate lives. So x-axis there, y-axis is there, and then what do we do to the x-axis to turn it into what's something inside of the y-axis? Okay, so that's what I did. So you took that line, the x-axis folded it together, maybe stretched it, and then put it inside of the y-axis. That's what has happened. Okay, much simpler with the linear function. So once again, I could think of this as my x-axis is as something that we're dealing with and transforming, and then what does it end up to be on the y-axis? So the graph is not really very revealing, but you certainly remember how things work. That's how they work. So every x produces a y. Okay, so that's the idea of the transformation. So one thing, let me get it started for you. 0 goes to 0. That's always the case with linear functions. Okay, so what else? What else happens? That arrow would be at an angle, right? So for example, 1 will go to 2, like this, right? And 2 goes to 4. So -1, where does it go? -2. Okay, so that's just another diagram, another way to visualize our function. But you can also now describe it verbally. Can you describe it verbally? What has happened? Stretch. It is a stretch. So x-axis is stretched by a factor of 2, but that's a detail that we can omit for the time being. So x-axis is stretched. That's it. Okay. Can you, following this idea, can you think of other things that you can do with the x-axis and the linear function. Where is that thing? Nope. No. Well, if we can stretch, can we shrink? Okay, yeah, a fraction of x. So can you give me a formula? So y equal 1/2 x. I don't want to plot the graph. I just go straight to what happens to the x-axis. So and this will be a shrink. So once again, 0 goes to 0. Okay, but the rest it goes like this from 2 to 1. From 2 to 1. And so on. Okay, so it's a shrink. So x-axis is shrunk. Okay. Okay. So how about this one? Y equal to negative 2x. What does that do? Reflected and still stretched, right? So reflected. Yeah, I guess you can say reflected. I prefer to think of a word that is more tangible, visual. So you flip it, right? So this one becomes, the x-axis looks like this. So the x-axis started here, right? And then whenever we did it, now the arrow is pointing in the other direction. So this is the image. This is the image of the x-axis, also known as the domain. I'm sorry, as the range. But also observe that that's the important part, which is you may easily overlook if you only look at one point at a time. You will overlook the fact that actually at this time x points in direction opposite of the assumed direction of the y-axis. It's pointing in the direction of decreasing order. But there is still stretch. So stretch, and flip, turn, whatever you prefer, how you prefer to describe it. Well, turns out there is a not lot more that can happen. And with the function of one variable, one output, one input, one number, numerical input, numerical output, and linear function, this all can happen because remember a linear function is in this setting is simply multiplying by a number. So whether we multiply by a number, say, let me put it this way, y is equal to kx. Okay, so cases. K larger than 1, stretch. Well, let me put it this way. K, absolute value K larger than 1 is a stretch. K is between 0 and 1, shrink. Okay, so that's if you multiply by 1/2, or you multiply by negative 1/2. Okay, so now K positive. Well, K positive. Well, let's say K negative. So K could be negative then. Also, not just what's happening, but in addition to stretching or shrinking, we have also a flip. Okay. So once again, absolute value larger than 2, so this could be 2 or negative 2, less than 1, 1/2, or negative 1. In either case, you have stretch, shrink. Okay, and then negative K multiplication by negative number flips the axis. Okay, what remains is to describe. There are two cases that are not on the list. What did I not cover? No, I meant values of K. Values of K. I did not include K equal what? K equals 0 to begin with. What has happened to this? What? What happens to the x-axis? How much? What? So what happens to the x-axis? So this is the x-axis. What do I do to it? What?
Points.
No. K equals 0, which means that I'm talking about y equal 0 times x, which is equal to 0. What is it? What? No, it does something. It is a point, right? So you take this x-axis and somehow turn it into a point. Okay, so that is an ultimate shrink. So you collapse. That's the word sometimes used. Collapse to 0. Okay, to 1 point. So the whole axis becomes 1 point. And when nothing happens, what's the value of k? Yes, k equal 1. So, I mean, it is y equal x, right? So nothing happens. It is entirely the same thing. So these are basic idea of what linear functions do as transformations, and then we'll have a similar but much more complex behaviors in high dimensions. Okay, so everything will remain linear within the course, but in high dimensions, every little thing becomes much more complicated. So just imagine, just for a moment, let's while we are looking at it, imagine what could happen to a plane. So if we are transforming xy plane to another xy plane, and we're still sticking to linear function, so we're not going to fold. That's the good thing about linear transformation. You never fold. What do you think can happen? You can still stretch, okay, but you can stretch horizontally, you can stretch vertically, okay? You can stretch diagonally, and then you can stretch disproportionately. You can stretch horizontally and vertically in not the same proportion. So, for example, then if you stretch proportionally, then a circle will still remain a circle. But if you stretch disproportionally, then you stretch this way but not that way, what happens to the circle? It will be an ellipse, yeah. Okay? So, one more important operation that you can, what else? What else? Stretching, shrinking, what else? Flipping. You can flip this way, that way. Sure. There's one more which you can never see with a line. Another operation. So yeah. Well, you can rotate. Yeah, that is a big deal. That you can actually rotate the plane as well. Okay, so they all have to be described appropriately with formulas. And that's where matrices come in. We describe linear operations rather than we having only one number to describe the whole thing. Now we'll have a whole table of numbers describing exactly these things. Stretching in that direction versus this direction, and then there are rotations, and all of these combinations of numbers will tell us what the function is doing. Okay, so I also want you to remember that we already saw something of that in pre-calculus, so I wonder if you remember anything about that. So more, say, I have y equal x squared, and versus y equal 2x squared. Remember this from pre-calculus? What's the relation between the two?
Graphically?
Yes.
One is stretched out or something.
That's right, stretched vertically. So this y equal x squared stretched vertically gives me 2y equal x squared. So multiplication by 2 once again does this thing, and it is exactly fits into what we have been doing, except instead of instead of stretching the x-axis and then seeing where it goes in the y-axis, that takes us to the next level. This takes to the next level because the transformation is a transformation of the plane. In fact, what is being stretched really? So y equal x squared, and this is y equal 2x squared. What has been stretched? That's right, y-axis has been stretched. Y-axis stretched, but also, just as I said a minute ago, the whole plane also stretched, but then only in one direction. So, and so is the xy plane. So once again, that's the picture in you saw in pre-calculus, but you can also think of it as a better capture the idea of what's happening is this. You take a circle, and then we stretch vertically but not horizontally, you're getting an ellipse. Okay? And every time, circles are helpful in that direction to detect stretches. What it does not help us with is rotations, right? So for the rotation, you have to maybe take a square and see how the corners that used to point in this direction now point in this direction. I just want you to see that once again, some of the transformation you saw in pre-calculus, but just not maybe not looking as deeply into what's going on. But once you think about functions as transformations, then this is the transformation. So this multiplication by 2 over here stretches the y-axis vertically and produces as a result also stretches therefore stretches the whole plane vertically, and therefore that's the effect that you saw. This is from pre-calculus. How the parabola becomes more slim. Okay, it stretches. So the important thing is that easy to overlook when you do pre-calculus, and this is described often exactly as I just did. Parabola stretched, but that's misleading. What's in truth happening is this: the y-axis is stretched, the xy plane is stretched. So this one is maybe not very descriptive because it's a piece of paper. I cannot stretch a piece of paper. So think about a piece of rubber, a sheet of rubber. Okay. So and then what is happening? What is the stretching? I replace xy becomes what it becomes x2y. Okay. So a point that used to be xy becomes moves to x2y. So that is a vertical stretch of the whole thing. So every point on the plane, xy, becomes a point on the new plane, and the y coordinate doubles. Okay, so once again, it's a piece of rubber, and so it might look like this, but you literally like this. You pull it up and down in such a way that notice that what's happening to under the stretch. What happens to the x-axis? What happens to the x-axis under this stretch? What? No. It stays put exactly. So nothing. Every point on the x-axis is not going anywhere. Look at the formula over there. So xy goes to x2y. So x is still there. All the transformation is vertical. Okay. You can similarly. Once again, something you saw in calculus, in pre-calculus, xy goes to, say, 2xy. It's the opposite. Then y-axis stays put. Exactly. It's like if you think about piece of rubber, sheet of rubber, rather, you like nail it along the axis and then stretch in the other direction. Okay. So that's exactly what this happened. This shows, and this one shows the stretch in the horizontal direction rather than the vertical direction. So that ellipse will become horizontal like this. Okay. So you might remember other transformations just worth mentioning. It is say x squared plus 1. What's the transformation? From y equal x squared to y equal x squared plus 1. What's the transformation? What? No, up. It is up. Yeah. So how would you describe it? Or you maybe already did. So let's just say it again. So y equal x squared versus y equal x squared. What has happened? It is a shift. It is a shift. So that one is easy. So literally, you have a piece of paper, you shift it up. So if you had a graph drawn on it, that's what pushes the whole graph up. But it's still a transformation. The only thing about why I don't want to talk about it more because it's not a linear transformation. So once again, linear transformations, the good thing about it is that 0 stays put. 0 always stays put. Whether you stretch, you shrink, you flip, or you rotate, the 0 will stays put. We only rotate around the origin. So that's where we want to within this confines will stay. Okay, so once again, these are what's happening to the xy plane, as you saw in pre-calculus for the most part, so not really in calculus. And that pretty much captures everything, but why didn't you see any rotations? Because, why didn't you see any rotations? Well, try to rotate the parabola, what's going to happen?
Changes the minus plus.
No, you rotate a little. How about a little? Not all the way, just a little. What's happening to the function? It's not a function anymore. Right, so then there is really no point of studying that way. But otherwise, you can imagine how you rotate a square and it becomes like this. Okay, so we will look into that. Okay, so what else? Stretching, shrinking, producing new functions, but through these operations. And certainly, let's not forget that topic that we have been talking about a little bit, that's composition. So the transformations are, if there is already a function, then the transformation of the x-axis or the y-axis, what is it? It's a composition. So you multiply over here, as you can see, you had y equal x squared over here. Okay, and then how do you get there in the algebraic sense now? Rather than geometric. What has happened is that you multiply, first you took x squared, and then you multiply by 2. That's a composition of two operations. Okay? If you, however, first multiply x by 2 and then take the square, so it's also composition, but the effect will be very different. What's the effect? First multiply x by 2. No, it will be. It means that there will be a stretching, or rather shrinking, in fact, along the to accommodate this function. You'll have to shrink the plane horizontally. So all of these compositions, we'll be talking about them a lot. So the problems are at least 2 problems on the homework were about compositions, right? So it will continue to be a big deal. Okay. So forming compositions. So no trouble with the homework in terms of compositions. So the idea of compositions is any particular manifestations maybe not as important as actually understanding what that composition is, a consecutive application of functions. So if you understand that, you understand functions, then you can do whatever that nature of the function is. You can combine them in the consecutive manner, and it's really not a big challenge. But we'll be reviewing it. So the example that I like to present to mention about compositions again is. Well, unfortunately, actually, you might, if you noticed or not, in the problem set, this is what you sometimes see. Something like this, and the problem is, and then you're supposed to compute the composition, either one or the other. So the challenge is then you don't know how to exactly substitute one into the other because the input-output variables do not match. So if for example, I want to compute this, the output variable should be, say, y, but then it has to come, this y has to come up over here and replace the x. That's what the substitution is. So that's often what the way compositions are presented, and it might be misleading. I think I was able to find problems or two in the set that they don't have this problem. But it is an extra challenge. So it is very easy to compute compositions when the variables mix. The output of the first matches the input of the second. Okay, so if f of y is equal to y squared and y equal g of x is equal to x plus 1, so what do you do to compute the composition f composition g? You just plug in, this is y, goes right there. So we know where it goes. So it will be what? x plus 1 squared, right? So I just substitute. I substitute y equal x plus 1, and I have a new function. That's all it takes. All it takes. The example that, and then this is what I was the point I was making, that you can go F composition G or G composition F. It is not necessarily the same thing. Can you think of an example?
What are not the same?
What?
The compositions are not the same.
Right. Yeah. So the outcome, yeah, of those two could be different. These two.
I mean,
Just these. Okay. So x plus 1 squared, and and the other one, what is it? X squared plus 1. Okay. So that is a very important observation that will be especially will come out in linear algebra a lot. That's how would you describe it? It is, a plus b is equal to b plus a times b is equal to b times a. Okay, remember how this is described? The word commutativity. However, compositions are not commutative. Okay, so that property applies to numbers. But with functions it's more complicated, and we sometimes simply do not have a commutativity. It is, in fact, to be expected not to have a commutativity of functions. Okay, so that's even with linear functions, that's still the case. So sometimes it does work out. Remember this: 3, 5x equal to 5, 3x. These are compositions of two linear functions, so it works out to be fine. It is commutative also. But in general, in high dimensions, it's not going to be the case anymore. Okay, so so now here's an important topic that we just discussed not long time ago, and that was once again linear functions. F of x is equal to kx. Kx, and remember k not equal to 0 versus k equals to 0. What does it tell us about the nature of the function from last week? So what's so special about k equals 0? It is constant function, but there was a more general. Remember?
Point.
No.
Point.
Yeah. So what's so special about? Just look at the graph. Y equal k, say 2x. What's so good about it? 1 to 1 onto, remember? Mm-hmm. So these are 1 to 1 and onto. And this one is not. Okay? And another way to describe 1 to 1 onto is no, I think there's one word actually to describe 1 to 1 onto. It is bijection, yes. I did not what I had in mind, but yes, bijection, one word that gives you 1 to 1 and onto. There is another word. Well, why do we care about 1 to 1 onto? Remember, the exponential function is 1 to 1 onto, which means that it's invertible. So functions that are bijections, they are 1 to 1 onto, are they invertible? In other words, they have inverses. So then k equals 0 naturally does not have the inverse because it's just a constant function. But for the rest of them do. And well, let's try to see how it works out. It's so easy in the linear case. Y equal kx. What's the inverse? Well, to answer this question is simply, once again, I want to keep the variables straight. So if my function is from x to y, y equal f of x, so y equal f of x, so x is the input, y is the output. I want to keep them straight, and so when I take the inverse, what happens to the variables?
They change position.
They change position. So whatever was the input becomes the output, and vice versa. Okay, but I want to keep the names. So just to keep it simple. So this time, y is the input, x is the output. Once you understand it this way, then how do you find the formula for the inverse? Take that equation over there and what? No. Just solve for x, period. So solve for x. So I have simply x equal y over, so let's say y equal x equal 1 over k y. Okay, so right away you can see how k not equal to 0 requirement comes into play, and it works out because k is not equal to 0. Firstly, secondly, what do we observe? What kind of function is this? No, it's linear. It's linear again. Just that coefficient is now 1 over k. Okay, so you might remember that's how you draw the. Remember how you find the graph of the inverse. So this is y equal 1/2 x. Very easy to find the inverses of linear functions, whether you do it by algebra. I mean, this cannot be any simpler. And geometrically too. Look at it. That straight line. Remember how I got one straight line from the other? This? No. Finding inverses geometrically. A flip about what? Well, about the diagonal, right? So flip. If you flip y equal 2x about the diagonal, y equal x, which is here somewhere. Y equal x, you'll have y equal negative 1/2 x. So that is a little bit misleading because once again you are flipping the names of the variables as well. So even though it is, you will see how much easier it is to think about both compositions and inverses if you keep the names of the function of the variables intact. So you know that x is input, y is the output. On the other hand, once you're looking at the inverse, the arrow goes in the opposite direction. So like. Think about this, the x-axis. Suppose we have the x-axis here, okay, and then we have the y-axis here. Okay, my function is, say, k is equal to 2, and then we already looked into that, so it is a stretch, right, like this, from x's to y's. And now we look at the inverse. With the y equal 2x is this green arrows. Okay, and now I go the inverse. This is the inverse. I reverse each arrow. And what am I looking at? I'm looking at a shrink, right? And it is x equal 1/2 y. So from y to x. So that is the relation between the function and its inverse. And it is reversing the arrows. So remember, we use the arrows to illustrate functions, pointing out from the input to output. And then you can see how the arrows reverse exactly to the opposite when you take the inverse. And now, but that's certainly not nice. Is a nice observation how stretching becomes shrinking and vice versa. But remember, the big idea behind the inverse is that they undo each other. So can you see it here? How you stretch and then shrink. That if you want to describe it verbally, but you can also you can take a trip. You can take a trip like this, and then back, and you'll come exactly where you started. Okay, so the one function, say f, and this is f inverse. Okay, and you come straight back. So this was x and this was y. We come back. So that's the idea behind the inverse. I just want a slightly more precise description of this. How do we describe this? If you remember the definition of inverse, Yeah, so diagrammatically it is described on the right, but what is the actual definition of the inverse? So suppose the function is one-to-one onto, then the inverse is a certain function which goes with the arrows go pointing in the opposite direction, not from x to y, but now from y to x. But how do we know out of all the possible functions of that nature, how do we know that what we're looking at is the inverse? It has a certain property that it has to satisfy. How do they algebraically express that idea is that the two functions undo each other or cancel each other?
The domain of
No, that's not enough.
F of like F inverse of x equals x.
F inverse, I think you're getting closer, but that's not the composition, right? So the two arrows over there, let me show you where is our trip. This is our trip. And that trip is from x to x. So let me write this trip. So I start with x, right? Then I apply f, and then I apply f inverse. And the result is x. So that is the definition of the inverse. Or is it? It's not entirely. What's missing? The other way around. There are two, that's half of the definition. Why? Because I can go backwards. So here on the right, I first went f and then f inverse. I could go in the opposite direction like this. Like this. Right? In the opposite direction. So in other words, no, that's not it. That's not it. I start with y and take a trip from the round trip like this. Okay? So that's the other one. So I start with y, then I apply, look at it, I'm applying what? Look at the picture. F inverse. And then I apply f. Once again, we're doing it from right to left, and the end result is 1. Okay, so this is the whole definition of the inverse. So starting with the function, making sure that it's one-to-one onto, and then a function that satisfies these properties is called the inverse. Okay, so there is a little of an issue here of why there is only one function like that satisfying this property, but it's very easy to take care of, and it works out just fine. Okay, so remember, inverses, whenever the linear functions, especially right now in the one-dimensional setting, is just too simple in order to require using all the complexity of the idea and of the definition of the inverse. But this is inevitable. This is we're gonna come back to this many times, because in high dimensions, really the definition will be useful very much so, like this one. So. Okay, so I guess time's up. So let me know if you have any trouble with the homework.